Hello, my name is Braedon Huber, and today I will be presenting on Stat 512 Project 3. To start out, the project is based on finding a multiple linear regression model to predict the concrete compressive strength. Concrete compressive strength can be described as the ability of concrete to withstand certain loads that will decrease the size of the concrete. In this regression model, there will be 8 different explanatory variables, and then the response variable, which is the compressive strength. Previous tests have been done to determine the compressive strength, which includes the artificial neural network. Now, this is used to develop models for a nonlinear system. Some of the explanatory variables for this model include sand, water-cement ratio, fine aggregate, coarse aggregate, silicon fume, superplasticity, and curing period. Later in this slideshow, we will be talking about the pros and cons of each different type of models. Now, an introduction of the explanatory variables are X1 is cement, X2 is the blast furnace slag, which is a substance that is formed when items are melted together. X3 is fly ash, which is basically the product of coal mixing with other gases. X4 is water. X5 is superplasticity, which is an additive used in all concretes. X6 is coarse aggregate. X7 is fine aggregate, which can basically be described as pretty much sand. And X8 is the overall age of the concrete. Now, for my original analysis, I just did a basic linear regression model with all the variables added. The first test I did, I tested for outliers, and I found through this box plot that variable X8 appears to have outliers, and there also appears to not be a multi-collinearity problem throughout the explanatory variables. The next part of my analysis I tested for non-constant variance and non-normality. Through the Shapiro test and the BF test and the normal QQ plot, I found that this model does have constant variance, but it also violates non-normality, which is a problem we will address later. Next, I used an added variable plot to test if any of these explanatory variables were unneeded in any way to predict Y. Through these plots, I found that X5, X6, and X7 appear to contain no additional information that is useful for predicting Y. And finally, I produced a type 1 ANOVA table and summary. After evaluating these tables, and their p-values, I found that X1 seems to be the most significant in predicting Y, and X5 and X7 appear to have no significant impact on predicting Y. Now, to fix the problem of certain variables not being needed or having an effect that is unwanted in the regression model, I chose to find a subset of the original regression model. And through the best subset algorithm, I found that the best model would be removing X5 and X6 to where it would be Y equals X1 plus X2 plus X3 plus X4 plus X7 plus X8. Now, after finding the subset, I did just a normal, I now I did an analysis of the subset and found that doing this does not fix the problem of the non-normality. To try to fix the problem of non-normality, I originally I tried to transform y and found that that actually makes it worse. So then I went through every explanatory variable until I determined that the only transformation that actually fixes the problem is when you transfer x8 into the logarithmic of x8. I then did a Shapiro test to prove that doing this transformation does fix the problem of non-normality. Now, after doing all this, I did a final model analysis. I started out by doing another type 1 ANOVA table and a summary, and found out that all the explanatory variables in the new model seem to be significant in predicting y, and also found out that the R-squared value does increase, which is a good thing. The next thing I did was to make sure there were no outliers and that all the variables were actually needed in the model and weren't just containing no additional information. So through this analysis, I found that x8 no longer has any outliers. And through my added variable plots, I found that all the variables none of the variables appear to contain no additional information for predicting y. And there's still not a multicollinearity problem. For my conclusion, I'll just go over what I went through throughout the presentation. I started out by addressing some potential issues, which was the non-normality and explanatory variables that were not needed for predicting y. I fixed them by choosing a subset of the original model and then transforming the x8 explanatory variable. And throughout this whole process, I also found that x1, which is concrete, was by far the most important explanatory variable. And my final model came out to be the concrete compressive strength is equal to cement plus blast furnace slag plus fly ash plus water plus fine aggregate plus the log of H. Now, a few pros and cons of artificial neural network and the multilinear regression model that I found was in the artificial neural network, the values do seem to have a significant deviation from the actual values. And in multilinear regression, there is lower flexibility in the estimates. And then some of the pros would be for artificial neural network, there is higher flexibility in the estimates. And for multilinear regression, it's easier to understand and it's a better looking model, I guess I could say.